comparing energy consumption of industrial sites. Not here. This one? All right. I'll be talking about comparing energy consumption of industrial size refrigerant system. Closer. All right. The reason why we want to do this is because that we think that we see a lot of noise when the talk comes to efficiency of different types of systems. I brought you an example of noise, which is not about efficiency, but we thought it was relatively fun. This is from a web page in Denmark where they are offering this movable air conditioning unit. The system is ecological. I don't know if they expect us to eat it when it stops to work, and it's using the environmentally friendly R410A. So yeah, that's noise, but on a more serious note, that we hear a lot of people comparing different types of systems, saying, oh, this system is so much better than the other, and those of us who calculate a lot think, what? And very often we see that many people give the competing systems some very distinct disadvantages because that makes their own system look better. Our purpose of this is to compare these the different types of systems that we see, and we think that as a company who is supplying to basically any of all these segments, that we are in a position to provide with a balanced view of all these different types. So we want to level the playing field. We want to be fair to everybody. We want to be equally fair to everybody. And one of the things we talked about was using what we call a rule-based selection of components. You can always make a system better or worse by putting on a bigger or smaller condenser or evaporator and so on. But we decided we wanted to say that we have certain rules for designing the size of the heat exchangers, the condensers and the evaporators. It would take too long to explain here, but it's in the paper what we decided. So we use rules for sizing of that. As far as possible, we used real component data that's specifically compressors, and we used some very complex models for the heat exchangers. We wanted to investigate the effect of the location, which is most specifically the ambient temperature of the location, and the sizes of these systems. So you could say, why not just measure a lot of systems that are already been built around the world? But we think there is a lot of variables in this that makes it a bit of a fuzzy picture. You could say, what was the purpose when you designed the system that you are measuring on? Was it designed for being the cheapest possible or the highest efficient? We don't know. Was the system actually constructed as it was intended to be constructed? You very often see a discrepancy in how a system is built. And what, very importantly, what is the state of the maintenance? Is it actually working? Is every valve working? Is some sticking? Is it full of air, full of water, and so on? So that makes a fuzzy picture. So we decided we wanted to do it with calculations as close to the reality as possible. We needed to limit our scope, so we said we want to look at systems that need to deliver a capacity at a low temperature at -25 and a medium temperature at -2. We would look at 4 different unit sizes or system sizes with the low temperature and the mid temperature loads listed here, and then most importantly, we wanted to look at different systems: CO2 transcritical in dx variation and CO2 transcritical in the flooded operation. We wanted to compare that against the 2-stage ammonia system with flooded evaporators. We wanted to look at a CO2 ammonia cascade, also with flooded evaporators, and finally, mostly for comparison to historical, let's say that, a 2-stage 507 system. we investigated all the systems in what we call a standard, which is, you could say, a bare bone installation that you very often see when it needs to be quick and dirty, and also in a variation where we tried to do all the optimizations that we could possibly do on those types of systems. And we evaluated this in 3 different locations. We chose Oslo in Norway as a relatively cold location, and Frankfurt in mid-Europe as a medium temperature, and Rome as a high temperature location. You could argue you could easily find a place that's hotter than Rome, but we think that the trend is very apparent with this location. So we used simulation software from a company called IPU, which is associated to the Danish Technical University. It contains a lot of system models already, and with those system models, controls you can specify, and different setup and changes in that. It has a lot of commercial compressors involved included in the program already, and it has some very complex heat exchanger models. And also it has ambient data for a multitude of locations throughout the world. What it didn't have was the industrial compressors, and we added them ourselves using the calculation softwares of suppliers. So what it basically does, it calculates how the system operates on an hour-to-hour basis throughout the year, and sums up the power consumption. So we started out looking at what we call a standard system for the transcritical. It was systems with dried gas coolers, no parallel compression, and no ejectors. The two-stage ammonia and 507 systems had open intercoolers, but it had no economizers on it. And the cascade, we started out with a cascade delta T of 5 Kelvin, which was, in our opinion, was the cheap solution, the cheap and fast solution, and no economizers where it was applicable. So we ran the calculations, and this is a lot of numbers. I will, in a minute, simplify everything a little bit, because the first conclusion we could draw out of this, that in general, the COP does not depend on the size of the system. There's some very small trends you can see there, and except for the smallest transcritical system, which was significantly worse, the COPs remained constant throughout the size change. I believe that the smallest transcritical systems was just an unfortunate selection of compressors from the suppliers that selected them for us. So, because of this, we will just, from here on, focus on the system that has 300 kilowatts on the low temperature and 900 kilowatts on the medium temperature. That gives us quite a bit less numbers, and it makes it a little bit more visible what we're trying to say. So this is the general result from the standard systems. You can see the bars are from left to right. That is CO2 transcritical in DX is red, and yellow is the CO2 transcritical flooded. The green is ammonia two-stage, the blue is the cascade, and the black is the 507. And the groups from left to right is Rome, Frankfurt, and Oslo. So you can see in the hot climates, the CO2 transcritical systems suffer. That is, I'm pretty sure, not a surprise to most of us. We could see that at best, which is in the cold climate in Oslo, they are at a 9% higher power consumption, and in the hot climate in Rome, they are at 45% higher power consumption than the best in the class. Mind you that this is a dirt simple CO2 transcritical system. We will look at it a little bit later if we optimize it. So some other consideration or conclusion out of this is that the cascade is not doing too good. But considering that we are at, everything is relative, but a relatively high temperature for the low temperature, the cascade has not yet come into its comfort zone of where it's performing the best. So it's falling a little bit behind. But if you would lower the LT temperature, then you would start to see the CO2 ammonia cascade come into to much better relative performance. Some of the things we talked about was, of course, we made some choices about the calculations during the setup, and one of the things that we we chose to do was we decided that we would have not have specifically load profiles, so that is the capacity of the system varying with the day or the production of a factory or whatever, because that would invariably lead to a lot of discussion. Yeah, but we have another situation, and so on and so on and so on. But we did try to put in a simple temperature profile for that was dependent on the ambient temperature. And you can see the two different results here. The green columns is with the constant load profile, and the blue column is with the variable profile. And you can see for most of the systems it does not really make a difference. But with the transcritical, we are actually favoring the transcritical systems a little bit by running constant load. And that has a simple explanation that if the load remains high during the cold season, then the CO2 system can have a higher percentage of its running time during the time that it's most efficient. Where in reality the load would drop and it would have a less running hours during the cold period. So we actually gave CO2 transcritical a slight advantage in our calculation. Yeah. The next is we decided that we wanted to look at systems that had a medium temperature capacity that was 3 times the low temperature capacity. What if it was the other way around? So we tried to flip it around, and you can see the ammonia 2-stage and the 507 2-stage are virtually unchanged, but the ones that has a CO2 compressor on the low stage has an advantage of this, and that makes perfectly sense. CO2 machines have a very, very good COP at the low stage, so that makes a little bit of sense. We decided to stick with the 300 on the low temperature and 900 on the medium temperature. So, yeah. So we can move on to the optimized system. So where we did what we could to optimize these systems, we added parallel compression on the transcritical systems. A small parenthesis is that the program could not handle parallel compression for the flooded systems, flooded transcritical systems, but I did some estimates of what it could mean later. We'll come back to that. We added adiabatic gas coolers, and we added ejectors to the systems. The other systems we added economizers where it was sensible, and we also reduced the cascade delta T to 3 kelvins, which in my point of view represents sort of the way you go when you want to optimize for efficiency. So here we see the same picture. A couple of things jump out. First of all, ammonia is in every situation actually the best refrigerant. That is nice to mention. But as the ambient gets cold and we have optimized the transcritical system, the CO2 transcritical is only a very, very small portion behind the CO2. behind the ammonia 2 stage. It increases again as the temperature increases, but in colder climates they are doing pretty well. So we have seen great success in the Nordic, in the Scandinavia countries. So that makes sense if you go all the way with optimization. There's one small thing that we should perhaps note, that the ejectors, they are only active when the gas cooler outlet is above a certain temperature, because then you have the pressure to drive the drive the ejector. So if you put in a hybrid or adiabatic gas cooler, then you are lowering the outlet temperature of the gas cooler, and then you are actually taking the advantage away from the ejector. So in an economic consideration, I think you would probably only be running with one of those tools at the same time. And since probably the ejector is the most cheap of those, then that's probably the way you would want to go. But in this case, we want to go all the way, so we are running with both of them. As I mentioned, the transcritical flooded system could not run with parallel compression, which actually gives you this a little bit of a strange result here. If you look at the Rome numbers, the CO2 transcritical DX system has overtaken the flooded system in efficiency. And that is surprising, but that is because the program itself could not calculate the parallel compression. But I did a few estimations where I said, okay, the gain with the parallel compression from the DX system, we apply that gain in percentage to the flooded system, and we get this result, which looks to me at least a little bit more realistic. And you can see also the CO2 systems in colder climates and also in medium temperature climates are actually down at a relatively acceptable temperature, while as the climate gets hotter, they are getting away from us. So I would conclude this by saying, yes, I have been talking about efficiency here. I recently saw a presentation in the US that gave a lot of good reasons to choose a CO2 to choose a CO2 plant. So efficiency is not everything, but the reasons to choose a CO2 system does not include efficiency. At least as the temperature gets just a little bit above the climate where I come from. So there are a lot of other things to consider: water consumption and water treatment of evaporative condensers and so on, safety for the personnel and products. Maintenance, I think that's still a bit of a gray area in with specific numbers for the transcritical systems. And installation cost, we have seen a lot of CO2 systems being offered at a price that is very much lower than a comparable ammonia system. But that also brings up what is comparable, because most of the CO2 transcritical systems are being offered by people who have their origins in the supermarket end of the business, and they have a significantly different view to what you would supply and the safety, not physically safety, but redundancy and so on, compared to the traditional ammonia contractors that has been delivering to slaughterhouses and dairies for years and know what it means if the system stops. So I see a difference in the scope of delivery, and I think that over time that the customers will demand more of the CO2 transcritical guys, But perhaps also the traditional ammonia contractors should consider if they are providing a Rolls-Royce when they should be providing a Volkswagen or whatever. So, so I think that the price difference will, over time, decrease. Maybe not go away, but it will decrease to another level. So, in closing, I would say that there's a place and a time and a situation for all types of systems, basically. So, so the future is wide open. Have a lot of fun. Thank you.